All right. Hi, I'm Nick, and today we're going to design an intake for a 2020 robot. So, to get a sense of where we're starting from, uh, we're starting from a detailed design of the drivetrain, of the hopper, and a space claim of kind of this ball tower thing. You can see that maybe this robot's going to be tall, um, and a shooter, and that whatnot. I'm picking this specifically to kind of talk about how you design things before everything is already made. So, kind of first step thing that I would expect any team to get done is their drivetrain. I'd expect somebody to get that done right away. Um, and Hopper is mostly a convenience thing because it'll be easier to see where some of the issues you can run into with that are before this. So what we're going to do is we're going to go and we have an intake. We've created a part studio. Let's intake. And the first thing I'm going to do just to kick everything off is to derive a whole bunch of parts. The reason I'm going to do this, and I would note while I'm doing this, this is a little bit dangerous to derive a bunch of parts here. The reason it's dangerous is because as things change, you could potentially get unintended consequences in this. And when we get through this, I'll show you kind of what I mean by that and how doing this can break your everything. So we'll derive a drivetrain rail, and then we'll derive. The only thing you really need from this is going to be the hopper floor. I'm going to grab the top though too, just because it is a little bit nice to do that. Since these are all derived parts and I don't want to actually use them, I'm going to make it really obvious that they're fake. And I'm going to change their appearance to something like really obviously wrong. Now I'll go like pink, right? So these are things that I don't. If these end up in my top level assembly, something's broken. I don't want them in the top level assembly. I'm using them because I want their reference geometry. Actually, the other thing I'm going to do is I'm going to grab bumpers here because bumpers are an essential part of doing this. The bumpers are going to be pink too because that's how we roll. So this is what we're basically going to work off of for making our intake. In real life, what I'd probably do, what I'm meaning to try actually, based on what 1678 has done this last season, is to break out some of these assemblies and keep them as versioned documents, which would help us avoid some of the breakage that I'll demonstrate later, either in this video or the next one. I'm not sure how long this is going to take me to CAD this all up for you. So the first thing I do on any design when you want to start off is we want our geometry master. And what this is going to be is the core geometry of this, of our design. And this is going to have a few important parts. So I'm going to sketch out. This is just going to be our floor. This is going to be about 2 inches off the floor. That should be good. And we have a few different core things we want here. So when you start with an intake, the most important thing about an intake, right, is that it's going to work for your game piece. So we got 7-inch power cells. I'm going to this tangent here, tangent there. What I found what we found in prototyping this year on 2220 was that a good distance from the floor on this was going to be about 6-ish inches. 6.5, I think, is where we kind of ended up. So I'll split the difference on that. And I guess we like to keep somewhat similar in there. So you can see that if I make this the same compression there, we have a dead zone here where it's not contacting the roller isn't contacting the ball and the bumper. So there's nothing forcing this up other than the ball bouncing up, which it actually does sometimes do that. But you can't necessarily rely on that effect. So I'm gonna boil this down. This also works. So 5 might seem a lot. That's like 2 inches of compression on a 7-inch ball. But remember that this is a bumper. The bumper is compliant. The bumper will squish a lot too. So this really ends up being less concerning. So we've got this one up here. We're gonna want another roller up here, and another roller up here. I'm going to slightly ignore exactly what this distance is. So these, I'm making these about 5.6 because if I remember correctly, that's where our like real ones ended up in terms of belt length. In reality, what I'd probably do is I'd go and I would look up, take a belt length calculator, and calculate how large those would be. I know that I'm from the design I'm basing this off of. I'm probably going to do 18 tooth 5 millimeter pitch pulleys. And if I remember correctly, 2020's robot this year had about a 5.6-inch spacing on them, which is just fine. Oh yeah, these guys are all going to be equal. So they're all the same size roller. A Versa roller with surgical tube going over it is about 1.5 inches, so I'm going to keep that. You notice I loosened up the spacing here, and then we're also going to one about here to like 6 inches. And then we have core things here. I'm also going to put a 1-inch, we call a beater bar out here. This is just something for stuff to run into before it runs into the rollers, which are flexible, which are, well, not flexible, very not flexible, so that you don't like dent your roller and need to swap out a roller in the middle of the match. You'd much rather like have a piece of tubing there. So what I found works really well for this is the small Andy Mark peanut extrusion. I think that's what they call it. Is really nice for this purpose. I'm gonna offset that like a 1/4 inch. And just to think about this a little bit, with an 18 tooth pulley, your OD ends up being about 1.25. I just want to make sure that this doesn't interfere with that. And I'm gonna just dimension from here. This isn't necessarily the best dimension to have there, but it's the dimension that I'm gonna use. And this should also be construction geometry. And then the way Peanut works is it has 2 holes here that are on, I think it's a 1/2 inch spacing. So those there. All right. So now we have, so this is what I would call, this is our, this is our deployed configuration for the intake. This is going to be a little bit, let's see here. Not going to worry about it too much right now. So here. Pretty often do a circular one. I'm doing a rectangle one because here just to test that out. All right. Now what we want is to also sketch it in its retracted configuration. Uh, this is important because that's how we're going to get make our linkage after this. And so we'll make those all equal, and then find that back there. And then I'll draw these lines. And the reason I do these lines like this, right, is because it's a lot easier than trying to do something weird with dimensions. And this is going to be that exact thing, like that exact set of bars there, which is what we want it to be. And then I'm going to do another sketch here. In this case, our bumper isn't exactly on frame perimeter line. So I'm going to actually dimension that relative to this, just so I make sure that we get that right. And this is just going to be something like stupid tall, because I don't actually care what the dimension is. There, get out of my way. So we've got this, and then we're going to want another rectangle here. And we're going to need to break some dimensions on this because the rectangle will rotate. This is why I like working with circles. Scat. And then I accidentally made you real again. So go there. And then what's the easiest way to do this? We could probably do this. So I'm a fan of drawing lines and just making them equal. This is because I hate dimensioning things. Sorry, that one's going to break things. So I really only needed that. Cool. So what I'm going to want to do is I'm going to want to dimension this so it's some safe amount in to 5. And then that's going to be hard to make something safe. We'll also dimension this edge to be maybe a little bit less, but still in there. And so then we have this, and I'm just going to give that a flat dimension off the floor. This isn't necessarily the best way to do that, but I'm going to do it this way anyways. All right, so we have our intake. You'll notice I didn't put the motor on here. The motor we're going to add later. In some cases, you might want to add the motor immediately, but I don't always do that. So then what we're going to do is remember, so we have, this is our gearbox here. So we kind of want to leave this zone open. So we're going to throw our pivot points kind of back here. I'm going to just going to be small because they're really just there to make our life a little bit easier. And make, yeah, 10's fine there. 12's probably fine there. Now we want to give it plenty of space off the top of here because run into things. Remember that these aren't in plane with our intake, our hopper. So we're going to worry a little bit less about whether they're going to run into things there. So we got those points. And then I'm going to put a point back here. And I'm not going to worry about it for a while. But I'm going to keep it here just because it's important to think about how we're going to deploy this intake. And frankly, if we don't, so I just like to keep it in here to remember, because your intakes cylinders or point actually no, I'm going to not do that. So the intake cylinder that we use is going to define where its point is going to be, and it's going to be somewhere back here. But it's not necessarily part of the core linkage, so I'm going to keep it off of this. All right, so now we have our core point there, which is great. And I'm going to now do our linkage master. So you remember from our previous videos, my previous video on basic linkages. If you watch that, if you haven't watched that, well, here's the quick rundown on how I do that. So we aren't going to worry about exactly where our intake pivots are in here. The important part is that these guys are all equal. And that use those. Make sure that we get this one. So and then two. So we've got these two circles pretty much represent our arms, the arms of this. And at this point, we can just dimension these to be something. So in this case, I'm actually going to do it a little bit differently than that, just because I want this to make sense. So this is going to get a dimension, and this is going to get a dimension. This one's going to be, just going to give that a plot dimension of 8 inches. And this one a plot dimension of 9.5 inches. And these may or may not be the best options, but they're the options that we're going to pick for right now while we take this out there. So I'm going to call this my linkage master. And you know, a key part of my linkage design process is guess and check. I am working on my linkage intuition of how things are going to work, but I don't have it totally down yet. Okay, so our linkage is going to be, I've been sketching this all on the center plane, but our linkage is actually going to be somewhere offset from here. I'm just going to leave this at 1 inch here. So this is going to be our intake linkage plane. It's going to be 1 inch for right now. I'm going to come back and change this later to make sure that it's something that totally makes sense. But the exact one doesn't matter terribly much right now. So we aren't going to worry about it. Let's make those construction. And the way these work. Decide exactly how we want to do the pivot later, but for now, 1 and 8 sounds great. Actually, I'm not going to make this all equal. I'm going to make these two equal and something less. And these two equal at like 1.125. The reason I'm doing that is because I think that these bottom ones, the way I'll probably be doing them is on a like dead tube axle, and these upper ones are going to be a little bit different. So I think that we'll be a little bit smaller on those. That's kind of detailing work though, so I'm not going to worry about it right now. And then just going to define these. And make a bunch of stuff tangent. Nope, not equal. Definitely not equal there. That doesn't work, Nick. Tangents all around. I'm a big fan of the tangent constraint. Makes my life very easy. So that's going to be our basic linkage. Linkage arms. I'm going to define another one. There's going to be another 1-inch plane. It's not really a 1-inch plane, but I'm going to come back later. The reason I do those is because oftentimes you want a little bit of space in between things for them to work well. And I am too lazy to figure out exactly what that is at this exact moment because we're just figuring out like core intake geometry stuff, which isn't necessarily. So these guys 875 because they're going to be Versa rollers. They'll offset a bunch of stuff. So there's different ways you could do this. I'm just going to grab these and then these two holes and just go with, I know that these are 1/4 inch, so we'll make them a nice free fit for 1/4 inch. All right, offset these. Some people like to do a little bit beefier offset off of things like this. I'm not super like, I don't know. We've been running 1/4 inch offset from stuff like this since last year on 2220, and I feel pretty comfortable with it. So not gonna worry. Oh, that was an accident. Get back there. Sorry, sketch out some more of that stuff. And then do our bumpers again. So I actually can't just make that straight. Sometimes depending on how stuff interferes, you can't necessarily make this a straight thing. And the reason you can't make it straight is because sometimes it'll like run into the bumpers or something. You can see that we're pretty close here to running into the bumpers, but we aren't quite there. So I'm not going to make this anything too fancy. And then you're going to have to sit through me tangenting everything. That'll be our cool. So we got those. Now we just need our base. Base is going to be down here. And we will do this as centers. And maybe it's a, I think it's a, be a 1-inch tube. probably. Yeah, we'll do a 1-inch tube. Give that a little bit of an offset because how did you do that? Silly on shape. And then we'll different ways we can do this. I'm just gonna do it this way. And let's grab like these center ones too. Different ways you can do this. Faster ways. I'm not going to worry about that too much right now. These are actually vertical, horizontal. So all could be equal. Finch. Got more tangents to worry about. Sometimes, like in this case, it can be helpful to hide stuff. I'm not doing it here because I think I know what I'm doing, but sometimes you might want to like hide these those bars or something. That'll be new. And we'll have another one on the other side, but I'm not gonna draw that one right now because this is enough for us to test out this linkage. Get it there. Need all our derived parts. Fix this, and then start constraining things. You notice I'm not worrying too much about exactly what these constraints are. We'll probably go back and fix them later. Good with that. Come on. And always make the last one cylindrical. Okay, so now we can kind of see what the range of motion on this thing is. We could see that we're going to probably have an interference issue back here. I'm going to go back and I'm going to, in this linkage master, I'm going to get a couple more dimensions for these guys in here. The reason I'm getting these is so I can grab that range of motion, which will define this. Oh, not offset. Let's see if this is right. So then we could see, so this is the full range of motion there. We can see that we have some interference issues that we're going to have to resolve. That looks on the whole pretty good. So let's throw that in our top level. And the benefit of how I did this, right, is that this is totally in place. So I can just fix this here and not actually worry about constraining it. And I can look at how this looks like it's gonna work around things. And that actually looks pretty good. You can see we're pretty close up there. But on the whole, that deployment looks pretty smooth. All right, I'm going to cut this video off here. In the next video, we'll kind of take this and detail it, show you how to do pneumatics for this range of motion, how we'll do detailing on this, how we'll add a motor into here to power everything, and all that. Thanks for watching, and have a good one.